Good afternoon, everyone, and thank you for joining us today. My name is Dean Lees, and I'm part of the engineering team here at Buckley Associates. And today we're hosting this webinar to talk about elevator hoistway pressurization controls with Jason Geegan from LFSystems. Buckley and LFSystems have been partnered together on this stuff for a few years now, and we got involved with LFS through RM Manifold Group. We really liked what they were doing. A lot of you might be familiar with a company by the name of US Draft Co., pressure-based draft controls for boilers. LFSystems is part of the same group, and they took everything that they know about pressure-based control and applied it to life safety systems. So Jason and his team are very familiar with pressure-based controls, and you know, they're really experts in this stuff. And you know, before we get going and I hand things over to Jason, just a few administrative items. We do have a lot of people on the line today, over 100 people registered for today's session. So everyone is going to remain muted during the extent of the presentation, but I do encourage everyone to ask questions as they come up. You can do that one of two ways. You can use the chat function, or you can use the question function in GoToWebinar. And we have some panelists on the webinar here that'll help to answer those questions. Jason, I may interrupt you from time to time if a good enough question comes up, but ultimately I want to encourage people to ask questions here. The whole goal of these webinars is for you, our customers, to learn these systems and understand how they function. And if you're thinking of something and have a question on something, there's a good chance that someone else does too. So please ask questions as you have them. And with that, I'll hand things over to Jason and let you get going.
Perfect. Yeah, and I'll echo Dean and thank you for your time this afternoon. We appreciate the opportunity to speak on today's topic. As Dean mentioned, we are kind of born and raised out of the pressure-based controls world. Started with draft controls. That is my background, is actually on the boiler side, with hydronic as a salesperson, as well as did a little bit of service work, a little bit of working for a contractor. So my father was a licensed plumber. This is all I've ever known, is the hydronic side of things and pressure-based controls. And as Dean said, it kind of has rolled into some other avenues, including life safety. So today we're going to talk about basically there's five goals, or five items that we're going to kind of cover. One is the goals of elevator pressurization. We'll talk about the standards and codes that apply, the different types of systems that are listed. We'll get into UL 864 and finally talk about how we have a solution. So we talk about the goals of elevator hoistway pressurization. There's primarily three reasons we pressurize our elevator hoistways, and the primary one would be to prevent smoke from flowing from the fire floor to other floors through the elevator shaft. That's the main reason. A lot of times, no matter what kind of a building you have, no matter what your evacuation plan is, you want to make sure that smoke doesn't get from A to B, right? But there's also the opportunity to use your elevators to mobilize first responders, and as well as use it as an evacuation for those that are unable to use the stairs to evacuate. And this mindset kind of started changing back in the early 80s when it came to smoke control and how to handle buildings. Back in November of 1980, there was a big fire at the MGM, and I should rephrase that. It actually wasn't a very big fire. It was contained to the lower floor. It did take out a bunch of the casino level, but the fire was contained within about 90 minutes. Unfortunately, there was no smoke control system in the building, so nothing in the stairwell, nothing in the elevators. In addition, the AC unit was not tied into the fire alarm system. So it didn't shut down return air ducts. It didn't do anything to prevent smoke from traveling from one point to the other. And part of that was there was a passive stairwell system, which we can talk about another presentation, but There were 85 people that perished in this event. Over 60 of them were in the stairwells, and it was due to smoke inhalation. So while the fire event was actually fairly tame, the smoke event, if you will, was very difficult to to handle. So we'll talk about some standards and codes. One, we're going to lean heavily into ASHRAE's Handbook for Smoke Control Engineering, specifically chapters 11 and 12. We'll talk a little bit about NFPA 92, UL 864, and the International Building Code section 909. As a kind of aside, we did do a presentation on stairwell pressurization, and it is on Buckley's website. If you go to buckleyonline.com and you click on the resource button, drop-down menu goes to online training, just search UL 864, and that will bring up the recording of the presentation. Alternatively, if you'd like to have a presentation on stairwell pressurization, contact your technical sales team at Buckley, and we can schedule either a webinar or an in-person presentation. Now, there's many things that affect smoke, the flow of smoke in the event of a fire. Primarily, stack effect is a huge one where smoke can travel up elevator shafts, mechanical chutes, trash chutes. In addition, there is a pressure created by the fire itself. When something catches on fire, there's a pressure wave behind it. And then if there's a sprinkler system, that water hits the fire, flashes to steam, which adds even more pressure. Typical building pressure profile looks something like this. The light blue line that you see here would be if there's no leakage between the floors, okay? You'd have the natural lift of the building. However, if there is leakage between the floors, it would actually look a little bit more like this squiggly line here. And one thing to consider, IBC 909 mentions this, that your building actually flips from summer to winter. And so in the winter time, the lowest pressure point is going to be the base of the building, whereas in the summertime, it's actually going to be toward the top of the building. So trying to balance a pressurization system for all conditions. I've been to Boston in both the summer and the winter. I know that New England has 4 seasons, so trying to set up something in the summertime to work in the winter or vice versa can be very difficult. So why are we talking about hoistway pressurization anyways? Well, IBC offers this as an alternative to elevator lobbies. In many cases, an elevator will open directly to the corridor, and there's no lobby to prevent the smoke from migrating into the shaft. So a hoistway pressurization is available to you as a designer. One thing to point out in 909.21, elevator hoistways have to maintain a min-max of 0.1 to 0.25. That's actually a little bit tighter compared to stairwells. Stairwells are a 0.1 to 0.35. So we'll talk about how to handle that. What are the 4 types of systems listed in Chapter 11? One is a basic system, the exterior vent system, a floor exhaust, or sometimes people call it the sandwich method, and finally a ground floor lobby system. So we'll start with the basic system. As you would expect, the basic system is pretty basic. You get a fan for each stairwell, a fan for the elevator shaft, you turn it on, and you get what you get. It's a fixed speed system. There's no control, there's no variance. You just get whatever that system was balanced to during commissioning. Here's a simple diagram showing the fan on the elevator shaft, fan on each stairwell. Now this is showing a bottom injection on the stairwells and a top injection on the elevator. That's not required. You could have a fan up on the roof for both the stairwells and the elevator. But when the fire alarm goes off, all 3 of those fans turn on, and you just, again, you get what you get. It's a kind of a blow and go system. But as you can see, note 2, in most buildings, the basic system does not perform well. This is so important, they actually place this twice, one in the notes and then once in the first paragraph. In most buildings, the basic system does not result in a successful pressurization. Kind of makes me think that they're not a big fan of the basic system, but let's find out why. If you look at the Contam example, you'll see where the system can work. If your construction is very loose exterior walls, this may work for you. The fan dumps a whole bunch of air into the shaft, but because there's so much leakage, it actually balances itself out. No matter how many doors are open, no matter what's happening, you basically maintain about the same amount of air. And again, the reason is that there's so much leakage that opening a door really doesn't change that. If you notice 6 and 7, your CFM actually goes up even though there's tighter construction. The reason for this is because, like I said, there's so much leakage that opening a door doesn't really change that. Whereas if there's no leakage or minimal leakage, the air actually wants to escape, and the force of the air actually draws more CFM. That is, if you can get the doors open. Because if you look at the maximum pressure on 6 and 7, it actually is over ½ an inch of pressure on number 6 and almost 2 inches of pressure on number 7. So again, the maximum pressure that you want to maintain is a 0.25. If you exceed that 0.25, the mechanism on the doors actually will not open. It sees it as a blockage and a safety mechanism to where it will not open. So while this is a cost-effective system, it only requires a fan. It's limited to just very loose construction buildings, but again, you have no control over what's happening. So you're really not. So whatever you balance it to during commissioning, that is what you get. So let's look at the second option, the exterior vent system. Unfortunately, the EV system works exactly like a basic system with one exception. Instead of the building always being leaky, you build a tight construction building, and then in the event of a fire, you open some dampers and make the building leak. That's the general gist of the system. You'll have vents on the exterior walls. Sometimes you'll duct those to the elevator corridor. And in the event of a fire, all of those vents open, and it creates a natural draw into the building to create this leakage. So when the fans turn on, it actually starts to push air out through these ducts or through the walls. And this is proven through the contam analysis. The CFM is exactly the same as the basic system. So there's really no way to, but you still have no control over this. So you have no way of knowing what the pressure will be under all conditions. So again, it provides a budget option for a tight construction, but it's the same as the basic system with more components and still no control, which means it actually does cost some more because you have all those dampers. And that's assuming that your architect or your building designer will allow you that much wall space for the dampers and that much ductwork space in the ceilings. Probably one of the most common that we see is the floor exhaust system or the sandwich method. This is really big, especially down in the Southeast. In the floor exhaust system, it actually uses less makeup air supplied in the shafts and the stairwells, but it also uses an exhaust fan to exhaust the fire floor, and typically a floor or two above it or below. And the concept assumes that you're exhausting smoke, so therefore you don't need as much air in the system, because if there's less smoke in the building, it's less chance of it propagating. The downside, excuse me, the chart is showing that yes, you do drop almost by half the amount of air needed to supply it. And it is a successful system in the analysis. However, there's a couple of concerns. While it can achieve the proper pressure, you do need multiple fans. If one of those fans doesn't operate, the entire system fails. Every floor now requires a control damper, as well as a custom-built logic control system to activate those dampers. So when the fire alarm goes off, that controller now has to know where the alarm is activated, open the proper damper, and then activate the proper fan, right? So obviously there's a lot of cost, a lot of custom work involved in that. If you exhaust the fire floor, it actually can draw fresh air in. Again, if you're pulling air out of a space, it's going to want to be replaced with fresh air. So when there's a fire floor drawing air out, you assume that that door to the stairwell will be open, so it'll naturally draw more air in to that fire floor, which could actually help spread the fire rather than extinguish it. And then the other thing is most sandwich method systems are designed for one fire floor. If that fire spreads, the system just doesn't know how to respond. So you design the fan to exhaust 2 to 3 floors. If you get into 4, 5, 6 floors now with multiple fire floors, again, it starts to fail. So let's talk about the final one, which is called a ground floor lobby system. Obviously, this system requires you to have a ground floor lobby, kind of in the name, right? So it does, however, have some potential for high pressure at the lobby doors. And ASHRAE actually mentioned that if this type of design is used, you need to contact your local fire marshals to make sure that these pressures at the lobby door are acceptable. Again, system diagram from the handbook showing your elevator lobbies and the ground floor here. You're gonna have a vent above the lobby doors. And basically, once the fan turns on, pressurizes the lobby, any excess pressure goes out that vent. There is several criteria you have to consider when doing the GFL system. If you look at the content modeling, there are 4 criteria. One, you have to make sure that your elevators on the ground floor do not exceed the max pressure. You have to make sure that you stay within range of all the other floors. You have to make sure that your stairwells maintain their pressure range. And you have to make sure that the lobby isn't overpressurized to where the doors won't stay closed. 17 different scenarios were run for the GFL system, and that's different conditions, different vent sizing, different conditions with the lobby doors. And as you can see, lots of different CFM variances based on those conditions. One thing to note that note 1, it says these flow rates, let me see if I can pull this up here. There we go. These flow rates were determined by using contam in a trial and airway to get the minimum pressure across the stairwell and elevator doors to be about 0.1 to 0.11 in H2O. So basically, it's just keep trying until you get it right in your modeling. So that kind of sums up stairwell and elevator fan sizing for me. I just wanted to kind of point that out, that we're not crazy when we say it's kind of a learn as you go type system. So here are the results of the 17 different simulations. I'll let you kind of take a look for a second to make sure you focus on that far right column, system performance, okay? If it says okay, that means it passed all 4 criteria. If not, it will tell you which criteria it failed on. And just to save you from counting, only 6 of the 17 different simulations passed. Okay, the first one had over 0.4 inch pressure, even with a vent at the lobby door. Okay, which means that while the lobby doors swing out, so actually that would maintain those doors open. It would push, that pressure would push those doors open to where you're no longer able to pressurize that space. Simulation number 13 fails all 4. So if that's your building, definitely wouldn't consider the ground floor lobby in that scenario. Here, what I did was I kind of combined the 2 charts together just to give you some observations. If you have an open door lobby, this fails. So going in and out of that lobby space, the system will fail. Number 2 and 4 are actually the same building, same conditions, just one is in the wintertime, one is in the summertime. So everything else is identical and it passes both conditions. So that's actually a really nice system for for that building. However, number 14 is that same building with that door open. So if you're going to use the lobby for any purpose during the evacuation, this cannot be used as an option. So again, it's a very simple fan and vent sizing or vent layout. So it's can save some costs, but it's limited by your leakage in the building. It can be very difficult to impossible. That's ASHRAE's words, not mine. Difficult or impossible to balance. and definitely should not be used if you intend to use your elevator hoistways as for the first responders or for evacuating those that can't use the stairs. So there's a fifth system. Like I mentioned, there were 4 systems listed in Chapter 11. Once you get into Chapter 12, it's called the Emergency Elevator Evacuation System. Includes the elevator evacuation concept. That's a lot of E's. I wouldn't recommend saying that too many times quickly. But the EEES includes everything involved with the elevator hoistway. So the elevator, the shaft, the machine room, the pit, the lobbies, everything else that's involved in the elevator is part of your elevator smoke control system. Just a few diagrams, simple layouts. The left 2 show a fan with a single injection into the shaft. One's at the bottom, one's at the top. The right side are actually pressurizing the lobby of the elevators to maintain smoke. So you can't get smoke infiltrating into the lobbies. This is a great option for if you're using an evacuation plan with the elevators, because now you have a safe space waiting for the elevator rather than just standing in the corridor. Some factors to consider: how long does it take to start up your evacuation plan? How long does it take to travel from the lobby to wherever the exit is? So if your lobby is in the middle of the building, your elevator's in the middle of the building, and you have to get to the exterior, how long does that take? How many trips will it take to evacuate the building or those you plan on evacuating via the hoistways? How many round trips? Number of elevators, and then just simple, the inefficiencies of the elevator itself, right? You meant to press lobby and you hit the 2, or you hit 4, or something to that effect, those types of human error, if you will. And there's actually a formula. It's a whole bunch of letters, numbers, and symbols that you guys can do on your own. And then there's some other things to think about. And this is for any system. You obviously still have to maintain your 0.1 to 0.25. You have to maintain pressure on the fire floor, right? That's the floor we really want to make sure that we're pushing back against the smoke. And then you have to maintain balance between your hoistway and your stairwell. So you may make your hoistways safe for either the first responders or the evacuation plan, but how does that affect your stairwell? So all of these systems we've talked about so far have relied on a single speed system. And again, whatever it was when you commissioned it, it is what it is, right? But remember, your building flips from season to season. So if you commission this in August and you have a fire in April, you may have problems. If you commission this in July and you have a fire in January, you may have problems. Okay, so we have to take that into account, not just for common sense, but actually according to IBC. And again, your balanced building through the leakage goes away once you pressurize your hoistway, right? It goes back to looking more like this. And by pressurizing the hoistway, you lose the benefit of air moving, air movement through the building, which is a good thing because you're now preventing smoke. However, if you overpressurize it, you start to look like this. Too much pressure in the hoistway starts pushing air and smoke back into the corridor, but also back toward the stairwell. So it now affects how your stairwell pressurization system is designed. So how do we fix this? Well, per NFPA 92, it's interesting. NFPA really digs into stairwell pressurization. There's a very, very small section about elevator hoistway pressurization, but the concept applies to both systems. A modulating supply airflow system will now change the amount of air that's put into the system purely based on pressure. So when doors are closed, there's one volume. Once doors open, we ramp the fan up and change that volume, okay? And this is a diagram showing really 2 options. One is if you put a fan directly into either your lobby, again, it's showing stairwells, but the principles still apply. You can do a bypass system for stairwells. The problem with elevators is because they're so much tighter of a window, you're just not going to be able to eliminate those spikes with the bypass damper system. And again, this was kind of discussed in an ASHRAE research project. And it's kind of funny. It says, it's concluded that the pressure compensated system is not needed for a fire scenario used in this study, as long as the door on the fire floor is closed for both sprinkled and non-sprinkled buildings. If the doors on the fire floor is opened, however, compensating system would help minimize smoke mitigation from the fire floor to the stairwell. Again, change the word stairwell to hoistway, same thing. So basically, as long as you don't open the door on a fire floor, you're fine. And it makes me think that we might want to have an access for the fire floor for people on that floor to get out. But if we do, a non-compensated system would fail under those conditions. So then we start talking about, okay, what does it take to make a compensated system, right? What are we required to do if we go that route? Well, IBC 909 says any mechanical smoke control system or elements thereof shall be equipped with a control unit complying with UL 864 listed as smoke control equipment. So then we dig into UL 864, and I could read 4 chapters if you'd like. That'd be really fun and exciting on a Tuesday afternoon. Better yet, we'll just look at this quick diagram provided by UL. It basically says anything inside the dotted box needs to be investigated and listed to UL 864. So any controllers, operator interfaces, your fire smoke control station or control panel. There's a box over here called the point logic controller. We'll get to that in a second. Outside the box, your motor controller, your VFD, anything that's controlling the motor does not need to be listed unless it's making decisions. Once it starts making decisions, it goes back into this side, right? If it's just a dumb device doing what it's told, like a VFD typically does, right? It takes in a signal from a control that says, I want to run at this speed. VFD, do what you're told. It does what it's told. That's just doing what that is a non-decision making device, so therefore it does not have to be listed. But the device telling it what to do does. That is the definition of a point logic controller. It is logically controlling something based on points of information, and that does require a listing. And one of the main functions of UL and that listing is something called circuit integrity. So just for kind of reference, most of my draft controls, my laundry exhaust controls, makeup air systems, they all have a simple start-stop contact. If you want that to run, you close that contact. If you want it to stop, you open the contact. It's a light switch. It's very simple, right? We all understand on, off. However, with smoke control and with life safety devices, we have to verify that what we are being told is what they want to happen. What I mean by that is if you want it to run, you have to close a run contact and open a stop contact. If you want it to stop, you have to open the run contact and close the stop contact. It's verifying not just through a single point, but through a dual point, that we are doing what we are told because that's what they want. And so most controllers on the market that are used for general pressure control is a single contact. By UL standards, where you're required to have a dual contact. So what does all this mean for LFSystems? Well, as Dean mentioned, we have a background in pressure-based controls from our draft control systems with US Draft, our laundry exhaust systems, and more recently, our stairwell pressurization controls. And we've created a UL 864 listed PLC dedicated for hoistway pressurization. We use multiple transducers, and we can be used with any fan rated for smoke control systems, except for in New England, it is only allowed to be green heck. That's a joke. Dean can pay me later. And so I introduce you the EHPS. If you joined us for our stairwell control system presentation previously, it looks very familiar because it's very similar. The E864 has a lot of the same algorithmic base as the L864, but there are some things that have to deal with response due to the piston effect and due to some, again, background things that really, I'm not even 100% sure of everything they do because it's not necessarily an external function thing. It's more in the background running. But if I put two of them side by side with no labels, you have no idea which one is which. Okay. But again, the system includes the controller, 3 transducers. We prefer to provide the VFD, not because that it's anything special, but because it is now programmed to match our controls. If you have a building that requires to use Allen Bradley, Danfoss, ABB, they have a specialty brand that they want to make sure everything matches, totally fine. Just know that that drive will have to be programmed by that provider to match what we need. Again, the E864 just showing a little bit closer up. 7-inch touchscreen, does have a dedicated input and output for the FSCS as required by code. This is a system diagram showing you kind of the different components. And again, this is just sample, but it could might be slightly mild. Zoom in a little bit here. So we have our E864 in the middle. We get our inputs from the control panel. All of our statuses as required by code go back to that panel. We get our power from the FSCS. We do have an optional output for Modbus. So if you want to tie this into your BMS for your weekly testing system to report, that would be a great option. Once we get our start command, we then send a signal to start the VFD, which then starts the fan. We verify operation through a pressure switch that yes, the fan is operating. And then we start to modulate based on the 3 sensors. We can modulate based off the highest, the lowest, or the average. On stairwells, we primarily focus on the low side. On elevators, we're more of an average just because of that piston effect. We want to make sure that those quick spikes are not necessarily taking over and changing things too quickly. We can have a relief damper at the base, which does help with some of that excess pressure as well. So when we talk about why we do compensated systems, right? And I kind of mentioned it in general, but just in a practical sense, if you are maintaining below your 1/4 of an inch, that pressure will kind of dissipate in your corridor. Now, if it's tied right next to your stairwells, that might affect it. However, if you start to exceed that 1/4 of an inch, you start to overpressurize your hoistways. It actually starts to push air and smoke toward your stairwells, and you can actually start to push smoke into your stairwell. Okay. So while the elevator hoistway controller does not necessarily directly talk to the stairwell controller, they do work in concert. If there's a blip of pressure on this floor pushing out of the elevator, the stairwell is going to say, okay, we need to put a little bit more air to make sure we don't push too hard, right? And we just keep back and forth. So they're kind of working in concert with each other to make sure that we're going to maintain 1/10 of an inch here, 1/10 of an inch here. If we start to get to the high sides, we'll open up a relief valve, or excuse me, a relief damper. We'll make sure that we maintain so that one is not overtaking the other. So how do you specify this? Well, we always recommend, the one question I always get is, well, who covers this control? We like to have it tied to the fan. Oh, let me try that again. There we go. When you're specifying your fan, just put it in the notes that the provide with LFSystems, VFD, controller, et cetera, et cetera. We also like to reference to the system diagram, which we can provide you in both PDF and CAD. So it'll have a sequence, it'll have the diagram, it'll have all the notes that are required. We can also provide a written specification for the control systems that you can tie into the rest of your smoke control system. Just to kind of recap some other topics that we cover, and if, again, any of these are of interest to you, let your technical sales team member know at Buckley, and we can schedule a dedicated webinar for you. But mechanical draft for fuel-fired appliances, again, growing up as a boiler guy, if you can naturally vent your boilers, please do that all day long. I don't sell a screw in that system. It's the best way to vent your boiler. However, as buildings get tighter and tighter, mechanical rooms get smaller and smaller, and space given for venting is always the last thing considered. And so you have to common vent certain situations, and that's where we come in to make sure that the appliances are operating within their optimal, not just within their, we can make it work. This is actually how it was designed to work. Combustion air for mechanical rooms, again, instead of having big louvers in the dead of winter that are usually covered up by the operators because they don't know why they're there, we can do a smaller opening with a fan and dump fresh air into the space to make sure you have enough combustion air. Wrong button, there we go. Commercial laundry rooms, everything we do on the boiler side, we can also do for laundry spaces. So dormitories, hospitals, hotels, laundromats. We can common duct laundry exhaust as well as the makeup air, all with one single controller. High-rise exhaust, if you get into kitchen, bath, or laundry for multi-family, multi-story, we can do the shaft, we can do the subducts, we can do the fans, we can do the controls, all pressure-based. It's a huge energy savings. So if you're looking for green technology and doing high efficiency operating buildings, that comes from less about the electricity and more about makeup air. The less air you're pulling, the less air you need to put back in. Our sister brand, KWUSA, this is a partnership with Kuster & Weaver. It's a German manufacturer for fireplaces, pizza ovens, kilns, coffee roasters, anything weird that you're just not sure how they need to vent. You can contact Buckley and ourselves, and we can help you with that as well. And with that, I am going to turn it back over to Dean. If there's any questions that we need to answer, I'm available to stick around and take care of.
All right, thanks, Jason. Let's see, we did have some questions. I had some technical difficulties here, so I didn't get to see the questions as they were coming up, but let me just get to the in here. Okay, let's see. First question, do VAV controller dampers need to meet the 75-second drive time, or is that only for fire and smoke dampers?
The short answer is I'm not sure. I would.
Yeah, I'm not either, to be honest. But we can do a little.
Yeah, we can dig into that. Yeah, we can. I say that honestly, that's more of a Dean question because that's more with the dampers that you guys deal with.
Just thinking about it, I don't think that it does, but we'll have to get back to you on that.
Yep, I agree.
Okay, next question. Do you have any input on existing buildings that have the elevators being modernized with passive ventilation systems as per previous editions of the 524 CMR that require 3 square foot or 3.5% of the hoistway per hoistway? I think there might be a typo there. But essentially, I think the question is, do you have any experience or input on buildings that are updating their elevators?
Sure. So
that have existing passive ventilation systems.
Yeah. So obviously, we would always recommend getting up to the latest, codes and standards, and that's where the basic system might work if that shaft is still has what you call leaky, below average leakage, if you will. But we, again, as a pressure-based controls company, we always think, even in that scenario, with some leakage involved, having pressure sensors and modulating that can slightly oversize the fan so that we make sure that we get that push. Again, if you run a contam and there's no need for those controls, I'm not going to sell you a box that you don't need. Mm-hmm. But to me, anytime just knowing, if you're going to refurbish the building and like you said, update those hoistways, in most cases, those do get sealed up. So now you're back to, now it's not a leaky hoistway, not a leaky building. It doesn't have that issues, or it doesn't have those, we'll call it benefits to use a basic system. So now you're back to, yes, we should have a pressure-based system.
Mm-hmm. Okay. Next question, what is the approximate price difference between standard BAS equipment and UL 864 listed equipment?
If a standard BAS contractor is building that and they're not getting it properly listed, then they might be more cost effective. If they are getting it properly listed, what we have found is between a 40 to 50% savings going with a prepackaged system from us. Where the issues come in is they just throw a pressure controller, put a comparator to it. I mean, I can do that for, very, very inexpensive, but it does not meet the code requirements. So, like I said, if you put it apples to apples, I'm going to be dramatically more cost effective just because it's prepackaged, it's done at the factory rather than on site with, custom programs and custom debugging and checking this thing and checking this, the other thing. That's already been done during our 9-month testing process to now we just, kind of rinse and repeat. The good news is though, is all of the, I don't want you to think it's just a cookie cutter system. Every default in our controller can be adjusted in the field during commissioning process. So while it is a factory prepackaged plug and play system, it can be adjusted based on the needs of that building.
Right. Very good. Next question, why is it Modbus and not BACnet?
The honest answer is because of licensing. BACnet is a different type of licensing, and because there's not a standard for BACnet, there's 2 different types of BACnet standards, and they don't talk to each other very well. So it's easier to gateway from Modbus to either one of those rather than pick one and then having to try and convert to the other on certain parts of the country. So Modbus is the easiest way to translate, and then it's also a licensing issue of having to pay 2 different licenses to the 2 different BACnets. And we can provide a gateway from either from Modbus.
Okay. And then the last question we have here, are all these systems for high-rise applications only, or do any of these apply to low-rise buildings?
So I would say that it can apply to a low-rise building. In most cases, anything under 75 feet, so 75 feet in most jurisdictions is the high-rise cutoff. If it's above 75 feet, you have to go into the high-rise code books. If it's below that, then you're exempt. So it can be used for a lower profile building. And we did a 4-story hotel as a very simple stairway system, and it was mostly just to make sure that it was kind of balanced throughout the seasons. That was their big concern, was modulating to maintain the balance. But yeah, so code requires you to at least review it over 75 feet, but it can be used for any building.
Okay, good. And we had a few more come in while you were answering that.
Awesome. Any
recommendations for elevator shaft construction, precast versus poured?
I do not. Your shaft option, the guys that'll do precast versus poured should be able to give you some leakage rates when discussing that, or what their expected leakage rate is of the shaft, but we have no preference. No.
Okay, good. And then do all the sensors, like temp pressure sensors, etc., being used for stairwell pressurization have to be UL 864 certified?
So it is, for us, I can't speak for everyone else, but for us, we are actually listed as a system. So our sensors have been listed as part of our package. So I guess in that regard, yes. Now, if you're doing a BMS contractor, again, they should get the proper listings for the system. And so I would say if you read, letter of the law per that diagram, which is this one here, that would actually fall into this thing because it's not making decision, it's just giving information. So technically the sensor doesn't have to, but whatever it is driving to does. So where this becomes an issue, primarily on stairwells, but I can definitely see it on elevators as well, is putting a sensor to a VFD and saying, well, the VFD is just a motor control, it doesn't have to be listed. Factually, that is incorrect, because that VFD is now using the internal PID loop, or point logic control system, internal to the drive. It's making decisions, therefore that has to be listed. And to my knowledge, there is not a UL 864 listed VFD available in the marketplace today. Now that could change, everything obviously constantly changing, but as of today, no one is offering an 864 listed VFD. And the fight will be, well, no, we're just a motor control. And that is what most of the drive customers or drive manufacturers will tell you. We're just the VFD, we don't have to be listed. But as soon as you put a sensor to it, and a lot of guys use the term smart drive, that smart function basically bounces it back over to here. So while the sensor doesn't require that listing necessarily, that control will.
Okay. We have more questions coming in here. How do you size the gravity relief?
So that depends on your testing standard and what you're comfortable with. So if some jurisdictions require, at least on stairwells, so many doors open, elevators, whether it's a ground floor open, and it depends on what you're being used for. So what we recommend is it's sized for the number of doors opened. So when they close, it has a place to go. So if you're sizing it for one door, that door is making up a number 3,000 CFM, then that should be sized for 3,000 CFM at so many feet per second, so many feet per minute, excuse me. And then it's balanced in the field. So it kind of boils down to, the system that you're doing, and we can assist you with that. Obviously myself and Dean, because again, that's more of a damper side of things than the control side, but we can definitely assist you with that. And I'll jump in again with kind of a more general statement. The good news is there's a lot of flexibility in how you design your stairwells and elevator hoistway pressurization systems. The bad news is there's not a lot of hard and fast, you must do X, Y, and Z. It's a lot of flexibility into how you do things based on local jurisdictions, based on building design, based on the type of doors you have. Again, if you use a single pane elevator where the door goes right into the walls, that's one way. If you do the single direction with two panes where they kind of overlap each other, that actually has a lower pressure threshold, because if you start pushing those two doors together, it sees it as a jam, won't open. So it really does depend on a lot of different factors to say you must size it this way. We can give you some rules of thumbs, and I say we meaning my engineering team, but it does come down to send us the layout, send us the the information, and we can kind of assist you from there.
Perfect. Well, I think we've reached the end of the questions here.
Awesome.
Thank you everyone for joining us, and thank you for all the questions, much appreciated. And thank you, Jason, for
absolutely.
Couple people had also asked about access to the slides and a recording. This webinar has been recorded. It will become available on our website, buckleyonline.com, under resources. And we will be following up with some slides along with some other additional information. And with that, I hope everyone has a great afternoon, and thank you again for your time.